In this lab, I've chosen to make a computer model to predict the time period for the motion of the Earth around the Sun. The data that has been used for this lab are the mass of the Sun, the mass of the Earth, the radius of orbit of the Earth around the Sun, and the orbital speed. I've tried to model the motion of the Earth around the Sun by assuming that the path taken is circular. The diagram shows the relative position of the Sun and the Earth at the start of the simulation. The Sun's position is at the center of the coordinate system. The Earth's initial position is at an x-coordinate of 1.5 times 10 to the power 11, while the y and z coordinates are 0. The centripetal force is provided by the force of gravity exerted on the Earth by the Sun. This force can be calculated using Newton's law of gravitation, which can be expressed as F is equal to G ms me divided by r square. The initial velocity of the Earth has magnitude 2.98 times 10 to the power 4 meters per second and is initially in the positive y direction. Using the force of gravity as the net force and Newton's second law, we will estimate the new velocity of the Earth at every time step. Newton's second law can be expressed as V final is equal to V initial plus F net delta t divided by the mass of the Earth. F net in this case is the gravitational force. We next come to the VPython codes for implementing the model. These are the first few lines of the program and set the mass of the Earth and Sun and also the initial conditions such as the position of the Earth and the Sun and the initial velocity of the Earth. The program was run for a time of 3.2 times 10 to the power 7 seconds, which is equivalent to some 370 Earth days. We now show the lines which implement Newton's second law. We will display the position of the Earth at each time step, and this will enable us to determine when the Earth completes one complete revolution. So let us now run the code, and this is what we obtained. The green line shows the path taken, while the yellow arrow the direction of the force of gravity. By observing the position data, we find that the Earth returned to its original position at a time of 3.188 times 10 to the power 7 seconds, which is equal to 369 days. So the prediction is about 4 days greater than the actual time period. One explanation could be the fact that we are assuming the path to be circular. The Earth actually follows an elliptical path. The same program can be used to model the motion of the Moon around the Earth. We simply need to modify the parameters such as the mass of the Moon, the orbital speed, and the distance of the Moon from the Earth. The simulation performed gave a time period of 27.7 days, which is 0.7 days greater than the actual value. It is again felt that the difference is due to assuming that the Moon performs a circular orbit.